He's a supply chain security at Google OSS security team. Please help me welcome him.
Hello, everyone. I'm Mihai from Ghost, Google Open Source Security Team. I also have the logo on my t-shirt, and I blog on mihai.page. You can see all my social profiles there too. So 2 years ago, we started seeing the future of the humanity become reality. We started seeing LLMs become useful. We started seeing developments on top of AI. Models became to proliferate everything. Everyone started using models. Everyone started building apps and startups and everything on top of that. But there was one small problem. We have all of these cool, super awesome projects, but there is that tiny piece from the XKCD comic, which is the AI supply chain security. Basically, how did the model get produced? How did the model arrive to us? And compared to traditional software, where you have a software producer and you get the software and you use it, for models, the situation is a little bit more complicated. You have big companies that are doing foundational models, that are training a foundational model on the entirety of the internet. And then you have the software engineers that are deploying the model into some application. But they don't just take the model from the foundational model and use it directly into the application. Usually the model goes through a fine-tuning step or multiple fine-tuning steps in process. And what usually happens is that there are 3 separate teams involved into this process, at least. So you have the first team at the big company that does the foundational training. You have another team of ML developers that do the fine-tuning. And then finally, you have the software engineers that actually build the application around the model. And the model doesn't go through from one team to the other via USB sticks. It's actually put into a storage and then taken out from storage, either private model hubs in the company or public model hubs like Hugging Face, Kaggle, NVIDIA, NGC, and so on. And there are so many places where an insider, where somebody malicious could actually alter the model. And you have the same questions about datasets. And this is not just theory. The last incident was a TikTok intern sabotaging another TikTok intern by compromising checkpoints on disk during the training process and then making the training process crash such that you would restart the training process from a compromised checkpoint and then you'll get a model that was completely malware, completely malicious. Okay, and even from the model hubs themselves, if you go on Hugging Face right now and search for Llama, you would find out that there are 2 different providers. One is Meta Llama and the other one is Facebook Llama. If you look just at the names, you wouldn't know which one of these models is the one that is actually the real Llama model. Fortunately, the other one is just a researcher, so it's not malware. But still, sure, if you look at all of the other information, like the stars, the number of downloads, and so on, you'll be able to find out which is the real one. But all of these metrics could be faked. Somebody could get a lot of bot accounts and fake all of these metrics to trick you into using the bad one. Okay, so going back 2 years ago, LLM caught the world by surprise. We got a lot of new development, but we still don't have a way to verify trust in the models or in the integrity of the models. And traditional approaches don't really work because models are a little bit different. They are not just one single file. There are so many model formats, and almost every few months there is a new model format that is being developed. And each time you do a fine-tuning to the model, some parts of the model change, some parts of the model stay the same. So we need to find a solution that would optimize hashing models, that will optimize signing models. I'm already giving some hints here, in such a way that only the pieces that change will be the ones that get recomputed. And finally, as a user, you might not need all of the files in the model. If you go on Hugging Face and look for, let's say, the Llama model, you would see that it has files in safe tensors format, in PyTorch format, Kaggle, and so on. But if you only use the safe tensors format, you only need about 1 file from there. You don't care about the other ones. So when you verify the integrity of the model, you actually verify just a subset of the files. Okay, so we had some questions that we sought to answer. Basically, who trained the model? Has the model been fine-tuned or altered since that point? And can you prove all of these claims? And similar questions about the datasets. Who cleaned the dataset? What transformations have been done on the dataset? And so on. And again, can you prove this? And in order to answer all of this, we can look also at the supply chain for a single train on the model. So you have datasets, you can iterate on them, you can do a loop. You have the train step where you get the dataset, you get the model source with ML framework like TensorFlow, PyTorch. If you are doing fine-tuning, you also get a pre-trained model that you put into this. You mix everything together, and now you create a new model. You put the model into the model hub in storage, and from there you either repeat the loop, you train another one, fine-tune another one, or elevate the model to production, and then from there somebody puts it into the application. And as you see in this diagram, at every step there are some risks, like compromising data poisoning, compromising the model storage, model poisoning, or even exploiting the model misprediction, like the recent incident with Grok on Twitter, if you are familiar, just this week. Okay, and model signing, the part that I'm talking about, is just the middle part here. I'm training the model, so I'm signing it immediately after that. And then each time I'm using the model, I'm verifying the signature. So when the model gets uploaded to the model hub, I verify, is this the model that you claim you're uploading? When the model gets elevated to production, I'm checking, is this exactly the model that you want to elevate? When the model gets used in production or for the next round of training, I also verify that. Okay, so today we have, as part of OpenSSF, Open Source Security Foundation, part of Linux Foundation, we have model signing released as v1.0. And also the model specification is extracted as a separate repository such that you can build tooling in other languages. Model signing is in Python, but if you want to build tooling in Go or Rust or C++ or whatever, you can target the specification and go from there. Signing and verification is finally here, and we are integrating this into frameworks and model hubs. So right now, I'm going to show a demo later. NVIDIA Model Hub already has models signed, and Kaggle supports signing via a feature flag. I'm going to do a demo for that. And we're going to also start expanding on top of signatures, as I'm going to talk about. Okay, so if you want to go to the model signing format, this is the QR code. We can sign an arbitrary collection of files, so not just models. We are expecting to be able to extend the same solutions to datasets and model cards and so on. And we don't depend on a specific key infrastructure. So you can sign with Sigstore, you can sign with certificates, you can sign with PKI, you can sign with PKS11, whatever, as long as it's supported by the library, you can sign in the same way. So basically we want to build provable integrity and trust in the AI supply chain, starting from the bottom with this one and then building on top. And if you want to go to the repository, this other QR code in here, plus some vanity statistics. Basically what we have right now is a CLI, so you can just test with a simple model, or a library that you can integrate with other tooling. So if I go now to the demo, I did yesterday at the lighting talk, I did the demo on how a model can be hacked. Now I'm going to just do the signing part. So let's do model signing, sign small model. This is going to sign the model with Sigstore. So I have this authentication flow to identify my identity on Sigstore. So I'm going to say, use my GitHub identity, get this code, and now the model has been signed. There is this model sig. That is the signature from the CLI. I could also train and sign the model at the same time. So let's do Python train and sign. So this one is going to train a TensorFlow model for digit recognition, and before the process ends, it's also going to sign it, such that you have the guarantee that the model that you are seeing has not been tampered with at all since training. And the YDC flow, again, GitHub, take the code, paste it in here. This is because I'm a human, I have to run this flow, but in a workflow, there is going to be the workflow identity that will be added to the signature. So I'm going to do one more demo for signing from the CLI. Sign with the key, and I'm going to say the private key is key.private. And I'm going to sign what models I have here. Let's sign the small model again. So this time, instead of signing with Sigstore, I'm signing with private key. And the only parameters that I changed were I passed here key and private key, the path to the private key. And I generated the signature this way. Okay, and now to show you how this works from a library, let's do Python upload.py. I'm going to say I want to upload the small models, and I'm uploading it to Kaggle. So at this point, I'm using the Kaggle library to upload models, which already has the feature flag integrated with the signing. And once all of these files get uploaded, there is this signing JSON, which is the signature that Kaggle generated for me with Sigstore. And at this link, if I go there, this is the model. Okay, ignore this pop-up here. Right now, Kaggle is verifying my model. So you have here Sigstore status pending. Kaggle is verifying that this is exactly the model that I wanted to upload. And if I look into the files into the model, there is this signing JSON, which is exactly the signature. You can inspect it. While Kaggle is doing the verification, let me go back to the slides. Okay, and actually look how the signature look like. So the signature is in the format called Sigstore bundle, which is basically a collection of signature verification materials so that verifier knows how to verify the signature, and an envelope that contains the stuff that I'm signing. Right now, the part that is important is the payload. That is what I'm signing. So let's look into the payload. The payload itself is another JSON document encoded with base64 that contains the name of the model and a digest, a hash for the model. And then the predicate is this model signing signature. That's the one that we extracted as a separate repository so you can target with Go, tooling, and so on. And then inside the predicate itself, we have all of the resources in the model. So all of the files in the model with their hashes, so like weights001 with its corresponding hash. And we also have the serialization method to know how to generate this, such that the verifier can generate the exact same hash. And I'm having this as separate because we also support for very large files. Instead of hashing a single file at once, you can shard the file into equal size bits and hash them in parallel. So there are two ways of computing a hash of a model to sign. And actually what we want to do in the future is be able to serialize on GPU. So generate a model signature on GPU, verify the model on the GPU, which can work even in the cases where you don't trust the CPU, but you trust only the GPUs. And also we want to be able to generate signatures over model cards in the same signature or as a separate file. Okay, so basically what we want to do in the future is make sure that all claims about the models are tamper-proof and tied to some identity, such that when you verify, you can say, I trust everything that comes from Meta. I don't trust models that come from, let's say, XAI. You can put that into your control plane, and immediately models that come from untrusted publishers will be denied. You won't be able to put those in production. And everything should be automatically generated by tooling that the ML developers use. So if ML developers use Jupyter notebooks to train models, Jupyter notebooks should be adapted to generate signatures and provenances for ML and so on. Okay, so let's go back to the Sigstore page, to the Kaggle page. And if I refresh this one, and everything worked correctly in the demo, I should see, okay, Sigstore status, it says that's signed. So the model, Kaggle verified that my model is exactly the one that I uploaded. The signature is valid. And if I go on this attestation, it's going to tell me a script that I can run to verify the signature myself. If you don't trust Kaggle at all, you can download the model, you can download the signature, and use the model signing CLI directly to verify the signature. But if you trust Kaggle, but you want to still verify, so in the trust but verify method, you just run the notebook itself. Okay, and going back here, slides again. Okay, so what we want to do in the future for looking at the full supply chain diagram for the models, we want to have this where every step, each time we generate some artifact, a data set, a model, the TensorFlow framework version, let's say, each time you generate some artifact, that one is signed. Each time you use it, you verify that. And then for every step into this process, you're going to generate a small attestation, a small document. And we are going to build tools that will be able to assemble all of these documents together such that you can go from a model back to the data sets that have been used to train the model. So, and the other way around. So for example, if a model is misbehaving in production, like it's saying you to put glue on pizza, you can look through all of this provenance chain and identify that this was because some Reddit dataset was telling you as a joke that you should put glue on pizza. But you can also go the other way. You detect that, you find out that this dataset that you have used in your organization to train models, you detect that it contains images that are illegal in this jurisdiction. Once you have all of this tooling, you can automatically detect which models you need to retrain, rather than you having to retrain all of the models or you thinking, yeah, I'm safe, and then having to pay a lot of fines. So if we have all of this tooling, that will all be helpful. And in order to do that, we actually need help from anyone that is interested into this. So if you want to help secure the AI supply chain, you can join the OpenSSF AI/ML working group. The next meeting is on July 14th at 1 p.m. Eastern Coast, 10 a.m. Pacific. Or for bigger organization, there is Coalition for Secure AI. Workstream 1 is also AI supply chain security, and we're working on a white paper on model signing and what we want to build on model signing and what should be the format and what are the personas interested in producers and consumers, what each one of them is looking at, and so on. We are expecting you, if you want to join either of these two groups, please welcome. You are welcome to join. Okay, so I'm going to finish the slides now. I'm going to run a larger demo after this. But the general idea is, let's make sure that what we build now, all the intelligent creations that we build today, don't have the security nightmares that we have learned in the past 30 years on traditional software of security nightmares and security incidents. Let's make sure we don't repeat them in the ML world. Okay, and let me switch back now to the demos. So right now, this is the NVIDIA NGC catalog for models. There are 123 models that are signed with the same solution. So let's say I pick one of those models. And once it loads, if I go to the file browser, it tells me that this model has been signed. 1.1 has been signed. These other ones have been released before the library has been available. So they are not signed yet. But now, because this is signed, you can download the model, you can download the signature, you can verify them once you have the NVIDIA private key. And now let me switch back to the Kaggle one, this one. So I have the signature here. And this signature can also be used to verify offline, so without having to run the tools. You won't be able to verify everything, but at least you can monitor that this has been signed by who claims it has been signed by. So if I go into the verification material, and I have these transaction log entries, I have this log index, which I can copy and then go to this page called search.sigstore.dev. Ignore that it says the email, I copied the wrong one. So I copied the long index, I put the long index in there, and this is going to tell me about the signing event itself. So it's going to tell me that when this model got signed, this was the hash of the attestation that was generated. So basically, the hash of the entire model with the predicate and the entire attestation itself. This is the signature for that attestation, and this is the certificate that Sigstore gave to me. The idea of Sigstore is that I don't need to maintain my key infrastructure myself and then worry about what happens if my key gets leaked. Sigstore gives me a certificate that is valid for like 10 minutes. So if you look on this one, on the validity, it's valid not before 8 minutes ago, and it's going to expire in 2 minutes. So I only have 10 minutes during which I can sign. After this 10 minutes, if somebody uses this certificate to sign the model, I don't care. It's going to be invalid. And actually, Sigstore itself makes sure that with one certificate, you can sign only one thing. So even that, you cannot reuse it. And then if I look also on Sigstore, on the subject, I have this email, which is the user ID on Kaggle as a number. So even if I change my user ID to, let's say, Meta, I cannot tell people like I released a model from Meta. And you know it's from Kaggle because it's the @privatekaggle.com. Once this feature becomes GA, it's going to be @kaggle.com instead of @privatekaggle, but this is right, still work in progress. And with this, you can still verify that these are models that you have signed. So now let me go. I'm going to copy this email, and you can find out how many models have been signed on Kaggle by me. So if I search by email and this one, I should see 21. This is how many times I ran this demo so far. But actually, you can monitor this, so you can create automatic monitoring, and each time your identity gets to release a new model, you can immediately get an alert. So if you know you didn't run the training pipeline, but suddenly there is somebody signing a model in your name, you know that something bad happened. Either somebody malicious ran the model in your organization, or somebody stole your identity on Kaggle and starts uploading models into your name. Okay, and now I can go back to the slides and stop for questions. I also added at the bottom thanks to a lot of other people that helped into this. Thank you.
All right, folks, if you can post your questions on the Slack channel, it's track machine learning, data science, and explainable AI. That will make it easier for reading. But if not, if you don't have your phone and stuff, I could take you on the mic. Do we have any questions? All right, I'll have a question. So I'm not super familiarized with like with the field, but one of the things that I was wondering is like, could you envision that in the future or near future, hopefully, it will be an absolute requirement that everyone has to have signatures, and that would not be possible to not work if it wasn't in that way, to avoid all these problems that could happen?
Yes. So there are already some legislation here and there that require, for example, software bill of materials. And there is also the equivalent for ML, AI bill of materials. And as part of this work, if we can automate the entire process, we can generate the AI bill of material automatically. So you don't have to keep spreadsheets of, I trained the model on this data set has been cleaned and so on. This tooling can generate it for you in maybe a year or two, depending on how much help you get. And for signature themselves, the model hubs themselves are starting to require signatures. Actually, the package manager, so like if you're uploading now something to PKI, they're telling you you should probably use trusted publishing or sign with Sigstore, such that people downloading the model know that, downloading the package know that it's exactly what you want to do. And we're aiming to do the same for models. Probably before legislation would require everyone to do this, because then it will be a scramble. But yeah, we're working towards a world where everything would be signed by default and verification would happen by default when you download.
Just a minor question. So you also showed, in addition to the signature, there is also certificates. Do they expire, or do you have to renew them?
The Sigstore certificate would expire in 10 minutes, but you don't care about it. So basically, you can view Sigstore as the equivalent of Let's Encrypt. So what Let's Encrypt build for HTTPS, Sigstore does for signing artifacts, signing objects. You get a short-lived certificate, you can sign once, and then you're done. With Let's Encrypt, you get a HTTPS certificate, and then 6 months you run a script and you get it another one valid for you without you having to take care of what happens if it expires and so on.
We have a couple on the Slack channel, so I'm going to cover those first, and then we'll go over the room. So one from Peter says, sorry, I might have missed the first few minutes of your talk, but how much overhead is there to calculate the hash based on a model? How does it scale with the model size, if it at all?
Yeah, so scaling with model size is almost linear because you have to touch every bit of the model. But if you parallelize it across multiple threads or multiple CPUs, that's why we split the signature into the files or the shards, you can reduce the amount of work. So actually using the sharded approach for very large language models, we got like 90 seconds more of saving time plus signing compared to just saving time, which was like 20 minutes. So it's 90 seconds out of 20 minutes.
All right, we have another question from Lauren. How does the identity part of the signature work when it is a company or other group producing the model or data set whose members are unknown or changing?
That's a good question. So what we're working on with Kaggle is to actually have every organization specify which members are allowed to publish models in that organization. And then you as the user, when you verify who produced the model, you can start passing in wildcards. star@kaggle.com or organization@kaggle.com, and the verifier itself will contact Kaggle and will know which are the members valid for that organization.
As you version the data, or as you use the signature to validate the data, at what grain is that data guaranteed? Is it the file? Is it the actual data structure? Is it the shape? Is it,
That is a perfectly valid question. We are still working on this. We're still experimenting. Join us as the OpenSSF forum for future discussion. But we're thinking granularity of every example into the dataset, also file, also the entire dataset as just one single blob. Each different granularity gives you different properties. Like when you append to the data, like if you have a streaming data, you would prefer to have it at item granularity. But if your data is static, you would prefer to do it once per the entire block. And we're also thinking about actually having two separate hashes, one for the signature and the other one to prove inclusion or exclusion, such that you can justify later, actually this data set didn't contain a copy of Harry Potter. Here is a hash of Harry Potter, perceptual hash of Harry Potter. You can look through the data set with a Merkle tree construction and you'll find out that that hash doesn't show up.
time for a few more questions. If anyone has other question, happy to take it. Going once, going twice. All right, let's help me thank our speaker, and then I think we have a break now, if I'm not wrong, or 10 minutes or so, and then we're going to be back in this room.